Hello, physical science students, and welcome to our new unit on electricity and magnetism. We're going to start this unit by talking about electric charge, and these are all of the items we're going to discuss in this video. So there are quite a few things we're going to look at. Let's go ahead and get started with what are electrical charges? How many different kinds of electrical charges are there? How are they transferred? We'll look at static electricity, that charge is conserved. We're going to look at different electrical forces, fields, how those compare to gravitational forces. We're going to discuss conductors and insulators, how charge is transferred, different ways. We're going to look at lightning, grounding, and electroscope. As you remember from middle school science, all matter is made up of atoms. And these atoms are composed of protons, neutrons, and electrons. And the protons have a +1 electrical charge. Electrons each have a -1 electrical charge. Neutrons have no charge, they're neutral. Neutral atoms have no charge because they have the same number of protons as neutrons. So they can be electrically neutral. In other words, they have a total charge of 0. That's what electrically neutral would mean. Amount of electric charge is measured in coulombs, and it's abbreviated with a capital C. Just to give you an idea of the size of a coulomb, or maybe an idea of how tiny and small proton and electron are, 1 coulomb of electric charge could be produced with this many protons. That's 6,250 million billion protons, a lot. Likewise, the same number of electrons would be contained in -1 coulombs of electric charge. So, important rule to remember when we talk about electric charge. Like charges repel each other. So protons repel protons because they are the same charge. And electrons repel electrons because they are the same charge. A negative charge repels a negative charge. However, opposite charges attract each other. So a positive charge and a negative charge will be attracted to each other. What do you suppose is happening here? There's some obvious charge attraction. I don't know if you've ever taken your laundry out of the dryer and they're sticking together. But there would be an example of opposite charges attracting each other. So the law of the conservation of charge is similar to our law of conservation of energy, our law of conservation of momentum, law of conservation of matter. Simply that charge cannot be created or destroyed, only transferred. Here's an example of some charge being transferred. Let's look at how that can happen. So let's look at a situation where charge is transferred. Here we have someone's shoe on the carpet, and if you shuffle around on the carpet with your shoe, these objects would be touching each other, the carpet and the bottom of the shoe. When those two surfaces rub against each other, electrons can be transferred. And here, if you look in this picture, the carpet has fairly equal amounts of positive and negative charge, but the action and the motion of the shoe rubbing on the carpet can allow some of the electrons from the carpet to transfer into the shoe. And you can see that here. We have fewer electrons in the carpet now. Those have been transferred into the shoe. When that happens, the shoe ends up with an accumulation of excess electrical charge. Oftentimes, this is referred to as static electricity. This also illustrates the law of conservation of charge because we have not changed the total amount of charge. We have only transferred the charge from one object to another. The carpet now has excessive positive charge, and the bottom of the shoe has excessive negative charge. But the total charge is still the same. Charges exert electrical force, and the magnitude of that force, how large that force is, will depend on two things. It will depend on the amount of the charge, and it will also depend on the distance between the charges. If we look at two charged objects, and let's just look at, let's say these are positively charged, and we look at another positively charged particle out here. This force will be much less, the repelling force will be much less between these two objects than these two objects, because this has a greater magnitude of charge. So these will have a greater electrical force, a repelling electrical force between them than these two objects. So let's look at the factor of distance now. If these two charged particles are really far apart, there will be less electrical force exerted between them, less of this repelling electrical force. If they are closer together, there will be a much greater electrical force between them. Also, it can be, this example can pertain to a positive and a negative charge. Obviously, the force then would be in the opposite direction. They would have an attractive force between them. So surrounding every electric charge is an electric field. An electric field exerts a force. We have two examples here, a positive electric charge and a negative electric charge. And these are the field lines. And for historical reasons and conventionally in science, the electric fields are represented by arrows that indicate how the electric field would make a positive charge move. So in this case, a positive charge would move away from this positive charge. So we draw the field lines for that electric field away from that positive charge. Over here, we draw the field lines with arrows toward that electric charge because that is the direction that a positive charge would move. So how do electric forces compare with gravitational forces? Well, we're going to look at two different situations here. One, we're going to look at atoms in particular. Here's just a simple structure of a particular atom. When we look at an individual atom, the electric forces in an atom are very, very, very great, and they're much greater than the gravitational forces for that atom. That is because an atom is a very tiny, tiny piece of matter, and the forces in between the electric charges between its subatomic particles are very great as opposed to the gravitational forces. When we talk about objects around you, macroscopic things that any object that you can see, the electric forces in those objects are going to be much less than the gravitational forces, and likely most objects that are around you are electrically neutral, in fact. So those forces are much less prevalent in the large objects around you and things that you can see and touch. Now let's contrast conductors versus insulators. You've seen these words before because we talked about them when we were talking about thermal energy. And matter can be a conductor of heat, or it can be an insulator where it does not, heat does not flow through it well. Likewise, we can talk about conductors and insulators when it comes to electrical charge. When we're talking about electrical charge, conductors are materials through which electrons move easily, whereas insulators are materials in which electrons are not able to move easily. Very similar to our thermal conductors versus thermal insulators. And again, in a similar way, metals are great conductors of electrical charge. Electrons move very easily through metals. As opposed to these items, here there's the metal part is a conductor, but this plastic coating around the wire is an excellent insulator, and I'm sure you could guess why. We don't want generally the wires to conduct electricity into your hand or into other areas of the building. We'd like that insulated, and we'd like the electrons not to move easily elsewhere. We just want it to move where we want it to move. Glass is an excellent insulator as well when it comes to electricity. So if you look at this cord, we've all plugged cords into an outlet, what part of that cord is an insulator and what part is a conductor? Well, if you said that the metal part is the conductor and the plastic is the insulator, you got it right. So far, we have only talked about charging by contact. When we talk about charging by contact, we're talking about transferring charge by touching or rubbing, for example, with the shoe on the carpet or the laundry, touching each other. And so charge can be transferred by direct contact between different objects. There's also something called charging by induction. Induction would be the rearrangement of electrons on a neutral object caused by a nearby charged object. An example would be here. We have a neutral metal sphere, and here we have another metal rod, and this rod is charged with only negative charge, excessive negative charge. When this comes close, when the rod comes close to that metal sphere, it charges this metal sphere by induction. Even though it is not touching the object, the charge rearranges itself in that metal sphere so that the positive charges are close to this area where the negative charge is. And the negative charge rearrange themselves so that they're far away from this negative charge, because these charges do not want to be close to each other. They repel. And that is charging by induction. So what about lightning? We all know this has something to do with electrical charge. How does that happen? Well, when a storm is occurring, there are a lot of convection currents within the clouds that cause charge separation. And they cause there to be a region of positive charge up higher in the cloud and a region of negative charge concentration that is lower in the cloud. When this occurs, these negative charges in the cloud repel the negative charges in the ground, in trees, in buildings, in anything that's on the ground, and they induce a positive charge on these surfaces below. At this point, these negative charges begin to move toward these positive charges on the ground and on the surfaces. And as they do that, positively charged ions will surge upward to meet them. They're very attracted to each other. And that when they meet, that resulting connection is the spark that you see as a lightning flash. Not only do you see a bolt of lightning, but you also hear thunder. How does this happen? Well, when when this occurrence happens, when a lightning bolt flashes in the sky, a tremendous amount of heat is produced. And that heat causes the air to expand very rapidly right around that lightning bolt. And that rapid expansion of the air produces the sound waves that you hear as thunder. So lightning strikes are very dangerous. Obviously, they can cause great injury, fire, loss of life, power outages. They can damage sensitive electronic equipment, and they can occur anytime a large amount of charge is built up in one area. So it's important to think about providing a path for that charge to reach Earth so that it prevents this charge buildup, this big difference in charges in different places. Earth is a very neutral object. It's very, very large, and it's a good conductor of charge. So grounding is the connecting an object to Earth by a conductor, via a conductor. Here's an example of a lightning rod acting as a conductor, which connects this lightning. It basically grounds it. It connects it to Earth. One more item to mention is an electroscope. It is a device that can detect electric charge. It does this via these two very thin metal leaves, they're called. And when these leaves are not charged, they hang straight down. When they are charged, they begin to come up like they are in this diagram here, because they are being pushed apart by the electrical charge. Here are the main points for this section. Like charges attract, opposite charges repel. There are two types of charges, positive and negative. Electric charge can be transferred between objects, but it cannot be created or destroyed. We know that. Electric charge is surrounded by an electric field, and that exerts electric forces on other charges. Charging by contact is transferring charge between two objects that are touching. Charging by induction is the rearrangement of charge in an object due to the influence of another charged object nearby. Advanced ideas. Why don't you research different types of lightning? Make a diagram or a poster illustrating them. What about statistical data involving the number of strikes that occur per year in Colorado, or maybe specifically in the mountains? Another idea would be to look at storm chasers. What do professional storm chasers do? How do they collect their data? What do they report on, and how do they show us their findings? So I look forward to seeing you in class and seeing what you have to come up with.